Last time we built the conveyor belt tf.data pipelines that keep batches flowing so the GPU never sits there starving. But a conveyor belt is only useful if there's a machine at the end of it. So today we build that machine. This is the build stage of our pipeline, the part where we actually assemble a neural network. And we're going to do it from the ground up. One neuron, then a layer of them, then a stack of layers, until we've got a working classifier. No magic, just weighted sums and a clever little squish. Picture the conveyor from last episode, batches of data sliding forward. Up to now the far end was a question mark. Today we drop the actual model onto the belt. Data flows in, predictions flow out. Let's open it up and see what's inside. Here's the whole secret of a neuron, and it's almost insultingly simple. Take your inputs, multiply each one by a weight, how much that input matters, add them all up, add one more number, the bias, which just shifts the whole thing up or down. That's a weighted sum. Then you take that single number and run it through an activation function. A squish, inputs times weights plus bias, then squish. That's a neuron. That's it. Now why bother with the squish at all? Here's the thing that trips everyone up. If every neuron just did the weighted sum and stopped, pure linear, then stacking 100 layers would buy you nothing. A line of a line is still just a line. The whole tower collapses into one flat linear layer. The activation is what bends the line. It's the only reason depth means anything. Take it out and your deep network isn't deep at all. The squish we'll use almost everywhere is ReLU, and you can learn it in one breath. If the number is positive, keep it. If it's negative, make it 0. That's the entire function. It's cheap, one comparison, no fancy math. And for reasons people argued about for years, it just works. It trains fast and it lets gradients flow. ReLU, keep the positives, 0 the rest. One neuron gives you one number, not very interesting. So we line up a bunch of them side by side, all looking at the same inputs, but each with its own weights. 64 neurons, 64 different opinions about the same 4 numbers. That row of neurons is a layer. In Keras, it's one line, dense 64. 64 neurons, each fully connected to every input. That's what dense means. Everybody talks to everybody. Now stack the layers. The first layer looks at the raw inputs and finds simple patterns. The second layer doesn't see the raw data at all. It looks at what the first layer found and combines those into richer patterns. Layer by layer, simple features compose into complex ones. That's the deep in deep learning. Each layer stands on the shoulders of the one below it. Here's the rule that saves you from 100 bugs. The output layer has to tell the truth about your problem. We're sorting irises into 3 species, 3 classes, so 3 output neurons. And because we want a probability for each, one final squish called softmax. It takes those 3 raw numbers and turns them into 3 probabilities that add up to 1. 3 classes, 3 units, softmax. The shape of the end is dictated by the question, not by taste. And once it's built, Keras hands you the blueprint. Model.summary prints every layer in order, the shape coming out of each one, and the exact number of parameters, every weight, every bias counted. 2,499 numbers for this little network. Those numbers start out random, pure noise. So building the thing turns out to be the easy part. The real question is, how do all those random numbers become right? How does it actually learn? That's training, that's next. Okay, let's build it for real in code. 04 and build.py, 2 pages. We'll load the irises, define the network with the functional API, print the summary, compile it, train it, and plot how training went. Every line on screen, nothing hidden. Here's page 1. Up top, the usual suspects, TensorFlow with Keras, NumPy, Matplotlib, and scikit-learn just for loading and splitting the data. We are not using it to model, only to fetch a clean tabular set. We load the 4 features and the labels, split off 20% for validation, and standardize the 4 numeric features so they're all on the same scale. Neural nets really care about scale. Unscaled inputs make training wobble. Now the network itself, the functional API, we declare an input of shape 4 measurements per flower. We pass it through dense 64 ReLU, then dense 32 ReLU, 2 hidden layers narrowing down. Then the output, dense 3 softmax, 3 species probabilities. We wrap the input and the output in Keras model, and that's the whole architecture. Read it top to bottom, and it reads like the diagram we just drew. Model.summary. This is the line that prints the blueprint. It lists each dense layer, the output shape, and the parameter count. Then the grand total at the bottom, 2499 trainable parameters. Sanity check that number against the picture in your head. If it's wildly off, you wired something wrong. Compile is where we hand the model its rules for learning. The optimizer is Adam, a solid default. The loss is sparse categorical cross entropy because our labels are plain integers 0, 1, 2, not one hot vectors, and we ask it to track accuracy as we go. We don't train here, we just tell it how to train. Model.fit runs it 50 epochs, batches of 16, validation set watching from the sidelines. It returns a history object holding accuracy and loss for every epoch. We pull the train and validation accuracy out of that history and plot both as lines. 2 lines climbing together. That's the picture of a model that's actually learning, not just memorizing. And there it is, a feed-forward classifier built by hand, layer by deliberate layer. You know what a neuron computes, why the squish matters, and how the output shape has to match the question. But everything we built started as random noise, 2000 some numbers, all guesses. Next episode, the payoff, how it actually learns, loss, gradients, and backprop. We'll watch those random numbers turn correct. See you there.